I'm also a member of IEC62351, the Technical Committee 57, Working Group 15, that is in charge of cybersecurity of protocols. Mostly the protocols that are involved into this cybersecurity process are 61850 and 60870-5-104 that are mostly used for automation of station. But we have a real case when we use this protocol to remotely control basically the volts used for gas storage. So here you can see the use case. Basically, during the winter, we use more gas in Italy. So we need to supply more gas than the one that we are able to provide. And since we had some gas as well that are mostly not used anymore because the gas is finished, so Italy decided to use this empty storage to push gas beneath the earth and to have more gas to provide it during the winter time. So basically we have two processes. The first one during the summertime, then that one that we use to push, and then we have the winter time when we use the gas. The goal of the project where we started to work was to provide the revamping of the remote control equipment. So basically we worked for the RTU side, and on the other side there was the remote SCADA. So we needed to improve the reliability of the data exchanged, and we needed to improve the configuration of self-diagnostic of the equipment that we were there to replace, because we wanted to provide an easy way to configure the plant and an easy way to signal if something is going wrong. And then, last but not least, cybersecurity. This is the reason why the people that was involved decided to use the experience in electrical field to use the 62351 to provide the end-to-end security in terms of protocol communication from the remote control system that are placed basically in Milan to the sites that are more or less in the north of Italy, but many kilometers far away. Okay, so here we have the devices. I'm going to explain you a little bit about the devices that we have, because we have 4 Ethernet ports that we use for the redundancy. So in case something happens, we are able to use another Ethernet port. Then we have the redundancy of the CPUs. Those are the CPUs on the left side. So in case anything happens, one CPU has another one that is able to provide the same features of the first one. So it's possible to hot swap and to replace the one that has, for example, an image with another one. And then we had the necessity to synchronize everything with the PTP. So we use this precision time protocol for time synchronization of the equipment. Same story goes for the power supply. There are 2 power supplies that are also redundant, so in case of failure, as well as before, it's possible to replace it. And it's possible to use, for example, digital input, digital output, analog input, and analog output to provide to remote SCADA system all the information that they needed, as long as the communication that were involved in the field process, for example, the CUA, but we will see that later. So the main rack is possible also to be extended with other racks that are communicating with HSR. So here we have an example of the design. So the very first 2 CPUs are used for the SCADA communication, and same goes for the field. All of the CPUs are used in a couple of 2 for the reason that we explained before, and are divided into 3 main areas. So the first one are used for the DCS communication, and then the second 2 are used to communicate with 104 to process that provide information about pressure of valves of pipes and other information like that. And the third one is used for energy consumption reports. Okay, so here in this architecture we can see how it works in terms of single point of failure of some equipment. That is not only the the one that we were talking before at the very beginning, but is also in terms of network communication. So if something happens not to the equipment but to the communication, in generally speaking, for example, the Ethernet cable or to the network switch, the communication is the communication that may go from here to there and then goes to the first VCS server, as well as it can go on the other side, and we can provide, in case of failure of anything at all, for example this switch or the server or the other switch, the communication with one of the redundant part of the system in terms of network communication. Okay, so as we were talking before, the communication started with the very first phase where there was no communication with cybersecurity protocols. We started with a simple 1.4 because we needed to analyze data, we needed to provide information if something was wrong, what happened, and we started with phase 1 only with 6087-5-1.4. I will refer it as 1.4 because it's like more simple, and the decision to use this one was mostly because there are some benefits, some advantages, and the decision to use it, even if not really related to oil and gas, the decision was because with this protocol it's possible to provide interoperability with more vendors. It's a standard, so as long as each device is certificate, it's possible to communicate with other devices that are certificated. It provides a redundancy in terms of inside the protocol itself. It's possible to provide redundancy because there are more communication that are up at the TCP level, but only one that is working with application level. So in case anything fails, the other link that is up goes it scales and becomes operative. And it's possible to provide data and measurements, so the flow of information goes to the SCADA as well as the commands from the SCADA to the control systems. And there are checksum and this kind of reliable data information. It uses a low bandwidth and provides information with timestamp. So for example, if some digital input moves, the information of when it moved is inside the protocol itself, as well as for time synchronization. And regarding the security, the cybersecurity, is part of the 62351, the role to provide cybersecurity to the protocol we explained before. For example, with part 3, it's possible to provide confidentiality. Part 3 uses TLS communication and mutual authentication of the devices that are involved inside the communication to understand if the device that is connected is really the device that you want to connect to, and vice versa. And it's possible to authenticate each command. So for example, if one person is sending like an operator is sending a command, it uses authentication to recognize if the person that is sending the command is really the person and it's authorized with role-based access control. Everything like that is provided by part 5 of the standard, and regarding the role-based access control is provided by part 8 of the standard. And the public key infrastructure is part 9 of the standard, and it's used to the enrollment of the devices to ensure that each device has a new certificate. And when you want a new device, you can rely on the public key infrastructure to provide the certificate needed. Okay, regarding the communication with the field, so we're not talking anymore with the SCADA side, but with the field side. The protocols that were involved in this particular project were OPC UA, and some of them were OPC DA. Then the other one that we are able to support are loanworks, like Modbus, basically TCP and RTU. 1.4 we explained before for the SCADA side, but as well for the field side, it's possible to use it as a master or as a slave. IEC62351 as well. This protocol is used for electrical communication, especially in substations. And then we have other protocols, for example, the LMS, the MP3, and the LoRa one for the IoT. We use this one to provide remote information from the plant to the RTU. Okay, regarding cybersecurity, we had another issue that was not only related to the protocol. Cybersecurity is not only the way that you speak, but involves also the hardware that you use. For example, if you write the password on top of the RTU or you save the certificate in a non-secure area, it's possible to anybody to go there and, for example, take the information that are related to the RTU and after that use it. So you need to ensure that the hardware that you use is secure if you really want to have end-to-end security. And to do that, we use some application processors that are provided with a lot of features. For example, it uses secure boot. So from the very first stage, when there is the boot of the operating system, it's possible to have a trust chain to be sure that everything that is running on top of the hardware is the real software that you want to run. It's not possible to execute another operating system or like a rogue operating system or an application service that is not the original one. So that's the reason why we decided to use the secure boot. Same goes for trusted execution of the software. It has to be signed to be sure that the software that is running is provided by the same person, the same company that provided the operating system, the device. Then there are cryptographic accelerators that are used from the hardware point of view to provide more fast system, fast access to data. For example, when the flash is encrypted. And there is also the tamper detection. Tamper detection means that if something's happen, for example, somebody tries to open a device when it's not supposed to be opened, or somebody take off the temporary battery, there is the first level that is a warning. But if you want to go further on, you can provide also a hardware way to delete and to erase everything that is concerned in cybersecurity. For example, in this case, can be the hardware key that is used during the boot process. This is the worst scenario at all, but it provides the most secure features. So, for example, in this case, when a tamper detection happens, it's possible to completely stop the execution of anything at all. So it's not possible to change anything on the hardware side. For the key protection, we use some TPM 2.0 the components that are integrated circuits on top of the board for have the hardware key protection. And we also use, we have a cyberpack basically that is in a collaboration with another company to provide information if, for example, somebody tries to attack, for example, if we have a man in the middle or this kind of information, we can provide alerts to the operators. We made it with another company. So we have been through a process of protocol certification regarding the part 104 and the 62351, as well as hardware certification for the environmental and material part, for electrical security, and for seismics. This has been required by our customer basically. So here we can see that we have some web pages. We use these web pages to provide information to our customer about anything. We were talking before to provide information if a tamper happened or this kind of stuff, and we use the web pages to provide this information as well as the communication with the SCADA systems with the 62351 protocol. And here the same things that we explained before with the role-based access control and the users are related to the information that are provided to the person that is logging on, and as well for the commands. So if you log in and you're not allowed to send a command, you cannot send a command at all. As well, we can configure the network parameters, the protocol configuration, and then for our information about the status of the RTU, about the communication with other protocols, for example on the feed side, if it's working or not, and the history of everything. So every point, every value, for example, that has historic, you can see the historic from this page, as well as configuration of the logic. And this one is an example of tool that is used for the configuration. So that's it. Thank you. If you have any question.